Hi, my name is David. I'm making this video for amateurs or novices or newcomers to the world of computer programming, and the purpose is to try and share and provide a framework for problem solving, a manner in which to approach any problem in the context of programming that will allow you to break it down, to get a grip on the problem, and provide you a means to tackle it. My intent is to have developed this method such that it's applicable in any paradigm, any language you're using, any computer, any operating system, all those kinds of factors. I'm hoping that it can help you in any situation when it comes to coding and maybe even in the world outside of coding as well. So obviously there's going to be similarities with your kind of generic problem solving type of modes, but in particular in steps 3 and 4, I'm trying to provide value in terms of how we think about approaching a coding problem. In particular, a coding problem in the way it's different from regular problem solving in day-to-day life. So, as you would normally do in day-to-day life, you want to make sure that you define the problem very well. Understand why is this needed. Pretty much the W5H, as they say, or we'll get to the H in the rest of them. So why are we doing this? That might entail what is the output that we need? What are the deliverables? Depending on the scale, this could be vastly different. If we need to make a simulation program, the output might be a huge program, which when run, it might take a long time to run, and it performs so many computations within it so as to give an output or a large number of outputs. On the other hand, we might be programming a small function where it's simply a black box. You put in a one number and it spits out one other number, and maybe there's just a few simple computations going on inside, but it's a kind of reusable and recyclable function which we might not want to call on in the future, and so that might be a small project there. So what is the output? What are we making? Or alternatively, what problem are we trying to solve? We might not know exactly what the outcome needs to be when we're starting. Maybe that will be developed along the way. So another one of the W5 is who? Who will be using it? If you're making something just for yourself, most of the time you can be pretty loosey-goosey with how you go about it in terms of your code's construction, in terms of how well you explain yourself in code comments, which are oftentimes included in the code to tell somebody exactly how it's working. Oftentimes, if you're making it for yourself, you know exactly how it works and you know how it goes wrong. And so you don't really need to worry about error handling because you won't be putting any bad inputs in because you know how it goes wrong. But if you are giving this thing for somebody else, they might not know how it works. So imagine if we have that black box scenario and this can only accept integers, let's say 1, 2, 3, etc. And now somebody tries to put in a 2.5, this thing might break your function. And then maybe that user will complain. Maybe it will be some catastrophic error, and that error will go downstream and have bad impacts on other things. So, in any case, understanding who is using it will provide a lot of context as to the level of resolution you'll need to employ in developing the solution, as well as how you want to go about presenting it. A lot of other visual elements and communication elements of your solution. Where? Will this be on your own system? Will it be on a foreign system? Will it be transferred by email? Will it be transferred by USB stick? There are other concerns. In particular, you might wonder about security. Where will it be used? There could be other questions that come up there. And you can continue asking these questions for the other ones. So, for example, what kind of I guess aligns with the I started off with why and then I said what. So yeah, what is the output going to be? What are we trying to do? That very much aligns with why. Who, what, why, when? Yes, when. When do you have a due date? Obviously critical. In any case, you get the point. Basic problem approach, like no matter what problem you're solving in life, you want to define the problem for sure. Next, I have here, identify the moving parts. What I mean by this is identify what are the basic inputs and outputs. So, for example, I'm going to use an example for the rest of the video, a very simple example, to illustrate how you can apply the method. So the example we'll use is sorting. So the example is going to be sort my data. Meaning, how would we go about making some sort of program which would take in some set of numbers? So let's just say 1, 2, 3, 4, etc. and spits out. Let's say this is the sequence. So we have our first number. So it's our first number. So its index we can say is 1. Second number, index is 2, 3, 4, etc. And then this corresponds to an actual input. So maybe 5.5. And this one's going to be 2.0. And this one might be -1. So we have this set of data, and now we want to sort it. So in our case, let's say sort is from highest to lowest. So 5 would be the first, so 1. And then, oh, well, it just so happens that I didn't mix up the order there at all. So let me say this one is 3. So now 3 is higher than 2, so our output would be 4. And 2 is higher than -1. So our output would continue from there as 2, 3. So that's highest to lowest in terms of the index, the sequence in which we were presented with this information. So how would we make a program to do this? All right, so let's identify the moving parts. In this example, the moving parts, and generally what I mean when I say the moving parts, is to understand what are the key inputs, what is given. And again, a lot of overlap with problem-solving techniques you might have seen in the past, especially, this brings to mind what I saw in my physics class or in high school. But again, steps 3 and 4 will really break it down for coding. So you want to know, though, what is given and known. What are the different dimensions? What I mean by that is the metadata. And what I mean by metadata is data about data, information about your information about your inputs. For example, I wrote down here in this array 1, 2, 3, 4, saying, oh, those are the indices which we're given. But really, what we're given, let's say, if what we're given is 5.5, and then I said 2.0, -1, 3, then we're not just given a set of 4 numbers. We're given a set of 4 ordered numbers. So the fact that 5.5 comes first gives us information, the information that this is index number 1, etc. So this is information about information. This is metadata. And this kind of sequencing and other things that might arise can be useful in solving your problem. For example, we might need to create a program that iteratively steps through a container, such as this. If we say this array is a container storing multiple numbers, we're probably going to need to peek into it at some point to pull those numbers out. So the fact of where precisely those numbers are is important to us. So this is what I'm talking about when we say what is given, what is known, what are the dimensions, what is the metadata, what is the totality of the information you're given. And this is totally dependent on the problem you have, and so it's hard to give more generalized description beyond that. But you want to be creative with really opening your eyes to what is the possibilities, like what is present. And in some cases, you might have to define your own data. You might need to decide on what you need and what you don't. And in that case, this kind of thinking about metadata can allow you to create more efficient products or programs, because more efficient in the sense that they can get more done with less. What I mean is maybe they'll need less inputs because they harness more data out of the inputs they're given. So that's step 2. Now step 3. Describe how to solve the problem with natural language, i.e. plain English, and narrow it down. So there's two things going on here. The first part, describe how to solve the problem, and then narrow it down. So I say narrow it down because there can be more than one way of solving a problem. So I'm going to come over here now with the white arrow. Redraw that line. You got to use my space out here. So when there's multiple techniques that you can think of, maybe just off the top of your head, if, for example, when I said, hey, sort my data, like reorder these from highest to lowest, maybe multiple techniques came to mind. Maybe you've watched those TED Talks about how to sort a library if you had to. And so what you should probably do is choose one, right? You don't want to rewrite the same code more than once if it's not necessary. It might be necessary because maybe you find efficiencies. Maybe the deliverable has changed slightly. Maybe it was in the wrong format. And maybe depending on what will be done with that output in the future, a different format might be a lot better downstream. So in any case, it can be difficult depending on what you know and what you don't know about the future and about what people are doing with your data. It might be difficult to choose your method. But typically, simplicity can be a pretty good rule to narrow down your selection. When in doubt, you can choose the simplest, so long as it works. Typically, if you're going with something more complicated, that's probably because the more complex solution creates some sort of nuance which you need. And if you need it, well, then really that's the simplest solution, isn't it? So what I also meant when I wrote down here, narrow it down, is that you want to describe your technique in as high a resolution as possible. High resolution meaning granular, meaning highly descriptive, describing every little detail. You're not going to start off that way, though. So when we start off, describe how to solve the problem with natural language. Well, we can start off at a high level. So let's say iteration 1. We want to sort my data, which is a sequence of numbers, 5.5, 2.0, negative 1, 3. Well, in fact, sort my data is the highest level. But that's not very granular. You might think it is at first pass, but I'm talking about getting down to really like the smallest details. So getting into how exactly you would do that. If I gave you these numbers, how do you sort them? Well, you might say then, let's say version number 2, let's use letter names to give steps. So A. You might say identify the highest, the largest value. And then identify B, etc. Identify the second largest value. Identify the third largest value. Identify the fourth, etc. You can just keep saying, repeat that step until you've basically just looked at all the values and said, in terms of which one's the first, the highest, the second highest, the third highest. And then you basically just denote your sequence, right? Done. Okay, that's still not high resolution enough. How did you go about identifying the largest value, the second largest, the third largest, those sub-steps? We need to know those details if we're going to put it into code. We need to know exactly what we need to be done. So instead, we might break it down like this. Identify the largest value. And then we might say step 2, or B. Remove that from consideration. And then C. Repeat A, B. Oops. Repeat A and B until complete. So the idea is we went from saying, simplistically saying, identify the highest value, identify the second highest value, identify the third highest value, identify the fourth highest value. Now you're done. We went from saying that to saying, identify the largest value of the whole set. Now remove that value from consideration from the rest of the set. Now repeat A and B with the remaining set. So we went from looking at all of these and saying, okay, 5.5 is the highest, and then removing that. And then looking at these three, saying, okay, 3 is the highest, removing that. And then look at these 2 is the highest, -1 is the highest out of itself. So you see how it's one more detail along the way breaking down those steps. Alternatively, you could have a different method. There's many ways to sort numbers from lowest to highest, highest to lowest, whatever the case may be. And it also depends on what tools you have available in your programming environment. So I'll leave that there for now, but just take with you the idea of breaking it down very granularly. The point you want to reach, the takeaway from this, is that you want to reach a point where all your processes are basically can be reduced to a few things. These include logical descriptors or comparisons. Let me just rewrite that there. And obviously this is going to depend upon which language you're within. So I'm talking about imagining you're coding in something like Python, something like VBA, which I've been working in and going to be learning more. So, but I'm pretty sure this is applicable to most environments and most problems you might want to be solving when you're creating your own program to do so. You're going to want to reduce it down to logical comparisons and logical or programmatic tools such as logic tools such as if statements, loops. So you want to reduce it down to simple statements within a frame where you can say, repeat this multiple times. Loops, and individual isolated actions or operations. And so that's what I meant when I talked about going down to a really granular level. At the beginning, if I say sort my data, there's a lot of sub-components. There's a lot of little tiny steps and comparisons along the way as we're kind of getting into in our third iteration of what our process looks like in plain language. Identify the largest value. Well, that could be broken down into more steps because how do you go about doing that? Maybe you have to compare that value against every other one. So is 5.5 greater than 2? Yes. Is 5.5 greater than -1? Yes. Is 5.5 greater than 3? Yes. So you can see how this can be broken down into basically all three of these categories. Let's do that quick example there. Identify the largest value. We can say if 5.5 is greater than all the other values, then the 5.5, you could say let 5.5 equal highest value, largest value. So of course this is still like in plain English. So you'd need to break this down further, basically until you reach a really granular level. This might be granular enough to get to step 4. And step 4, so here's our if statement, and here's our comparison, greater than, as we saw over here, logical comparisons, and then our action, which is to assign a variable, to assign something. That's an example of an action. There can be so many different types of actions depending on your environment. So lastly, we can talk about enacting the process that you've created in your coding environment. So this obviously is where the magic happens, and as such, because I'm trying to make this method applicable to just about any environment or any scenario at all, it's going to be hard for me to describe what this might look like here, beyond some overviews. So essentially, what you need to know is what tools are available to you in your coding environment. So for any given language or environment, that's going to be composed of things such as your data types. So for example, obviously you might be familiar with very basic data types that are used just about everywhere, which are things like integers. Integers are different from floating point numbers, which are sometimes called doubles, sometimes called floats. There are nuanced differences that I'm kind of brushing over. Strings, which are collections of characters. So any word, anything you'd put quotes around is a string. Like you wouldn't put a quote, quotation marks around a number 45, right? That's a number, right? There are times when you'd want to. For example, what if you had a phone number? We had a phone number 999, etc. That's not a number you'd want to add or subtract or multiply. That would be meaningless because a phone number it's not the kind of number you add. So a string is anything, obviously, like words, whatever the case may be. And other data types as well. It could be things like a Boolean. A Boolean is a binary, so that's either 0 or 1 type of thing. So there's more. You're probably familiar with some of those. Then you want to know data structures. Data structures are tools you can work with. You could think of them as containers to store data, which allow you more opportunities to work with them. They allow more flexibility. They allow more nuanced approaches. So for example, you might have something like an array, which I've mentioned here. So typically, in my experience, arrays will be organized such that you have an index value, which corresponds to some other value. So essentially an array, for example, will start off with index 1, and here we have value 5.5. And here we have index 2, value 2.0, etc. The point is that you can simplify reference to information. You can simplify reference to data by using a index value as the means to refer to it. You can have all different kinds of data stored in an array. Another type of structure could be an object. If you're in an object-oriented paradigm, then an object could itself be a data structure. So an object could be, well, that's a very vague statement. What is an object? So many things are objects. It's very abstract. And that is very applicable. That is the case because it really is that abstract even in coding environments. So an object could be, really just about anything. But the idea is that an object is something to which you have assigned attributes. So, for example, if we say a car is an object, a car has attributes of color, make, model, whatever the case may be. These are attributes. And it has methods. So these are actions that an object might perform. So methods for a car might be, turn on, or accelerate, or slow down, or consume fuel, that kind of thing. Another data structure could be a list. A list might be very similar to an index where you have, some sort of list item number and then the value. Maybe lists could be for strings only, that kind of thing. It's all dependent upon which coding archetype you're in, or which coding paradigm you're in, which language you're using, what's the environment you're in, that kind of thing. So you need to find out what data structures are available to you, because typically data structures are the key to doing any kind of really higher order operations or more efficient operations. Data structures are super critical. So get a handle on those. Next, you'll want to know what are all the logical methods available to you. And that includes functions as well. So, as we mentioned over here earlier on, we have logical comparisons as one of our um, granular level resolution at which we want to arrive at with our instructions. We want to know, since we want to reach that point, since we want to be able to say, I have described my instructions using all my logical comparisons. Well, then you need to be sure that you know what your logical comparisons are. So obviously you have things like equals, greater than, less than, like these are the most basic you could ever encounter. But depending on your specific type of, your specific coding environment, there might be not so obvious things like comparisons you might use between objects, for example. Since objects are not simply numbers, they're not simply strings, etc., these might have comparisons that you might not be aware of just off the top of your head, or just as a beginner, just starting in that archetype, that paradigm. Functions are huge. You got to know what functions you have available. A function, in case somebody doesn't know, is essentially just a black box which takes an input, as we discussed off the top of the video over here. A function, generally speaking, takes an input, does something, and gives you an output. So you might say it does something 1, you put in a 1 and maybe it gives you 2. So that function might be multiply by 2. Or it might be plus 1. Or it might be add 1. So we don't really know just going off of this information. But the point is, most of the time you'll be writing some code and you need something done. You need maybe a transformation to be performed, like give me the square root of this, or give me if we're talking about a matrix, if you're familiar with matrices, give me the transpose of a matrix, or give me the determinant of a matrix. These are more complex operations that mathematically you wouldn't want to have to do them manually every time if it's something you're going to be doing often. So there are just so many functions in just about every paradigm you're going to be in. There are oftentimes functions that you can get from the net, custom functions that people made for themselves or for reference, user-defined functions which you can use. So those can be very helpful, and oftentimes you'll want to look around and see what's out there. It's pretty much like you need to know what functions are to be coding effectively, because they are the tools in your toolbox. If I were to give you a toolbox, if I were to tell you, hey, I have a leaky pipe in my house, can you fix the pipe in my kitchen? And you didn't have a toolbox, well, what would you do? I mean, you can't just fix it without any tools. You need maybe a wrench, maybe some soldering tools, etc. So without functions, you're dead in the water. So make sure you just go around, look at what's out there, do some Googling, look through the libraries, whatever the case may be. And the last thing I'll comment on here, enacting the process in your coding environment. So far I've been talking about what tools do you need? What do you need? Like, what is the base knowledge that you need about your coding environment, right? But now when it comes to enacting the process, what I would point out here is that enacting the process is not always as clean as you might like it to be after having made this list of instructions, after having broken down your problem into exactly, here's how I solve my problem. What I mean by that is that given the nature of your problem, enacting the process as you've described it might not be possible. What I mean by that is that sometimes things you say in natural language can hide hidden complexity. And that complexity might demand that you have to perform many more functions to do it. So we saw that here with the word sort. The word sort hides the fact of a much larger description, which is something along the lines of sequence my data. And then sequence means, put in order. And it might sound like these are just synonymous, or this is just a different way of saying it. But that's because this is a simple example. There are many times when something that might sound relatively simple, maybe just take a sentence to say in plain English, there might not be some sort of pre-made function for it in your coding environment. It might not be so simple. The point is, when you are breaking things down to this high level of resolution, high granularity, there might have been something that you left as one line, like here's a one-liner, do this. But that one line, in fact, in coding, in your coding perspective or situation, it turns into many more lines. So that's something to watch out for and keep an eye out for. And the last thing I'll mention is that when we enact a process in a coding environment, we're inevitably going to need more data than we originally started off with. If you remember, we said define the problem, identify the moving parts. And we said identify the moving parts. We have these knowns. We have one array and this metadata, which is, it's not really like variables that we're getting. It's just information that we know is there. And so the idea that I'm sharing is just that, definitely just be comfortable with the fact that you're going to have this array. Obviously, you're going to be manipulating it. But in the process of doing whatever problem that you have, for example, as we talked about here, identify the largest value. Here we have like a variable called largest value. In the process of solving your problem, you're going to create work in progress info, work in progress variable, work in progress objects, whatever the case may be. Just don't shy away from that, or don't ever think that it can be avoided in solving the problem. That's just part and parcel of the process. And you can think of variables generally if you're in a coding environment where you can just define variables, define storage for placing things as you're solving a problem. You can think of variables just as scrap paper. If you're on a math test and you just have some complicated problem to do, you're going to use scrap paper. You're going to be writing all over the place, and you can do that with your variables. You can use things to store intermediate results, that kind of thing, whatever the case may be. All that really matters, if you're not thinking about efficiency, is the output. Of course, when you get to higher levels, efficiency might be really an important consideration. So that's something to think about when you get there. So I'm going to leave it there. I hope that this has definitely added some value or been helpful to you. Again, trying to come at it from a pretty abstract level, high level, so that this is applicable to just about anywhere. But I do believe that there's value in that, in having a roadmap, in having a framework. I think that without a framework, you can't get a grip on a problem. So, like I said, hope this was useful. Thanks for watching. And if you'd like, you can support my videos on Patreon, where supporters can get access to all my code with comments, lots of comments, so that my code is basically self-explanatory with the degree of commenting that I have. Hopefully that's valuable. And I'd even be willing to code with for you. So thanks for watching, and take care.